Hello and welcome. In this video, we'll be looking at an application of neural networks for supervised classification. The goal is reservoir characterization. And in this specific example, we're going to be using surface drilling data to tell us something about electrofacies, variations in the subsurface. And the this specific Jupyter notebook is based off of this paper, which was published in the SPE journal way back in 2020. And we are applying this to the Volve data set, which is a data set that was provided by Equinor. And I've provided a link to that data set as well in this Jupyter notebook. All right, so just to give you some background to the problem, in general, geologists or petrophysicists would look at a well log, and based on the variations in the certain well log, say the neutron porosity and the sonic travel time and the gamma ray and the bulk density, they might identify different facies. So you're looking at a track over here, which represents the different facies as we go from the top of the log all the way to the bottom of the log. And these facies were determined by looking at the variations in the gamma ray log, the sonic travel time log, the neutron porosity log, and the bulk density log. And typically this is something that's done by the geologist or the petrophysicist, and it is a time-consuming and resource-intensive uh, procedure. Anyway, so we are given these facies, and the question we're asking ourselves is whether drilling data that we collect at the surface, whether that is sensitive to these variations in these different electrofacies. And in principle, the answer is yes, because when we are talking about surface drilling data, we are talking about measurements or calculated values like rate of penetration, weight on bit, torque, RPM, and other quantities. And uh, those quantities are essentially manifestations of what the bit is doing as it is drilling through the rock. And it stands to reason that different electrofacies, which are characterized by different log responses, may also have different mechanical properties and therefore may have different manifestations of those properties in the drilling data. And so the question we're asking ourselves is, can we construct a classifier that just looks at this drilling data and is able to identify these different facies? So that's our specific task. And this is something that we could very well do with logging while drilling or measurements while drilling uh, tools. And the question is, why wouldn't we use something like that? And why would we instead rely on noisy measurements acquired at the wellhead? Well, if you think about a measurement while drilling or LWD sub, they're typically placed about 30 to 90 feet behind the drill bit. And so the information that they are reading is going to be delayed with respect to what the bit is currently doing. And the information that they relay up to the surface is also going to take some time. And so in the end, what's going to happen is that the information that MWD or LWD subs provide us are probably quite a bit depth delayed with respect to what the bit is doing. And if we want something that is almost near real time, then we should probably harness the information content of surface drilling data. And when I talk about surface drilling data, we're talking about measurements like rate of penetration, weight on bit, torque, equivalent circulating density, uh, RPMs of the bit, and things like that. So moving on to the problem, our specific problem, and this is the data set, the Volve data set, which consists of 15 wells, of which 3 wells are exploratory wells and the remaining 12 are development wells. What we have here, and the Volve dataset is based off of a North Sea field, and it actually did produce roughly about 63 million barrels over its lifetime. And this matrix scatter plot over here essentially shows us the problem that we are facing. We have rate of penetration, we have weight on bit, we have torque, and we have RPM, among other measurements. And we have these points colored by the facies labels. There are blue points, there are the orange points, and there are the green points. And we want to take this information and essentially construct a classifier that relates these facies to the input features ROP, weight on bit, torque, RPM, equivalent circulating density, downhole pressure, and things like that. So that's the problem that we're facing. So it's a supervised classification problem. Since we're dealing with 15 wells, which were drilled at different periods of time, we are going to make a few assumptions. One is that uh, Equinor used the same bit and the same drilling crew over all of these 15 wells. Or in other words, we're going to minimize the influence of different bit types or make the assumption that those differences are minimal. Okay, so what do we have so far? We have our surface drilling data, which consists of 6 or 7 features. We have, and these are data points that are recorded at every half-meter interval. And for each of those depth values, we also have the corresponding facies, which was mapped out by, say, a geologist or a petrophysicist. And now we're going to construct a classifier that relates them both. All right, so going down, we're going to first import our libraries. And for this specific example, I've already collected the data and put it into a .csv file. And I do want to mention that this was work done by some of our students, Ishank and Nok, quite some time back. They were the first authors on the paper that I'd linked to earlier. So we're going to read the Excel file directly, and we have a whole host of measurements. In fact, we have 23 different attributes associated with each data point. We have the well uh, name, which is just a set of numbers, 1, 2, 3, 4, all the way to 15. We have the depth. We have the gamma ray values, photoelectric factor, sonic travel time, rate of penetration, weight on bit, downhole temperature, torque, and various other measurements, as well as the volume of quartz, volume of shale, volume of carbonate, and the associated facies label at that depth. One thing to keep in mind is that the measurements of mineralogy, which is the volume of quartz, volume of shale, and volume of carbonate that was made on these samples was only done in the exploratory wells. So for the first 12 wells in this data set, which are the development wells, there is no mineralogy data. But nevertheless, we can, for the exploratory wells, see what are the predominant minerals present in each of the facies. So if you look at that, we can look at the volume of shale. associated with facies 0, facies 1, and facies 2. And you can see that facies 2 is predominantly shale as opposed to facies 0 and facies 1. And if you look at the calcite content or the carbonate content, you can see that facies 0 is predominantly carbonate, while the rest have a little bit lesser carbonate. And facies 1 is predominantly quartz. So that's what we have in terms of the mineralogy. And because there is a variation in the mineralogy or differences in the mineralogy, we also have the differences in the log responses. And that's why the geologist was able to capture those differences by just analyzing the log responses. All right. So we have 15 wells in this data set. Only the first 12 wells contain the input features. That's the drilling data and the facies labels, which are our target variables. So we're going to select only the first 12 wells. And specifically, we're going to select only the features that we're going to be working with, which is the well name, ROP, weight on bit, torque, RPM, mud flow, equivalent circulating density, downhole pressure, and the facies label. And largely, what we can see over here is that most of the data set, uh, uh, what we can see over here is the univariate statistics associated with each one of the input features. What we also observe is that the weight on bit has a few negative values. We also observe that the torque has a few negative values. And in general, any of these variables, if they have negative values, it's typically not associated with uh, the drill bit action on the rock, because a negative weight on bit essentially means that you're pulling out of hole as opposed to applying some force on the bit to drill through the rock. Whereas a negative torque essentially means that we might be entering a stick slip situation. Uh, and so those negative torque values are not very informative about the lithology. And same thing with the negative weight on bit values. So we're going to clean up our data set. We're only going to be selecting the positive values associated with our input features. And again, it's a good practice to check if you have any missing values. We don't have any missing values. This is a very, very well behaved data set. But now let's take a look at things on a well by well basis. We are trying to construct a classifier that's going to look at all of the data in aggregate. And the data comes from 15 different, 12 different wells, the 12 development wells. And we want the data to essentially occupy the same range. And what do I mean by that? We don't want any one well or couple of wells to be associated with anomalous RPM or torque or weight on bit values. If something like that occurs, then it's probably because of some problems while drilling, or it may be because of a choice of a different drilling company, or it also may be because of a different drill bit, among many other possibilities. Okay, so let's look at rate of penetration on a well by well basis. So we have well 1 all the way through well 12, and I don't observe anything unusual in terms of the rate of penetration, which is in terms of meters per hour. Largely, most of the wells occupy pretty much the same range, and there's nothing unusual. Let's look at the weight on bit. And with the weight on bit, again, for wells 1 all the way through well 12, we're observing pretty much the same thing. Let's look at torque. And when we look at torque, yes, there's quite a bit of variation across all of the wells. Um, and while some wells seem to occupy specific ranges, what stands out to me, at least over here, is well one, which seems to be associated with inordinately high amounts of torque. And I do not know the reason for this. But in comparison to the other wells in this data set, that seems unusually high. And so perhaps it may be warranted to remove well one from this data set because that unusually high torque value could be because of maybe poor wellbore cleanup while drilling. And so if the cuttings haven't been removed, and uh, that can lead to high torque values. And those high torque values are not informative about the lithology, or rather they're not informative about the what the bit is doing while it's drilling the rock. The torque that we're observing is because of poor wellbore cleanup. Anyway, that's well one. Let's look at the RPM as well. And when we look at the RPM, again, we see huge variations across all of the wells, but largely between wells 1, 2, 3, 5, and then all the way through 12. We see that they occupy pretty much the same range except for well 4, which has unusually high RPM values, almost by a factor of 2. And that makes me question what was happening in well 4. It's entirely possible that this could have been a completely different bit. It could have been a different crew or many other possibilities. And so if that's the case, then it's also a closer examination of well 4 is warranted. And maybe if we don't find an answer for that, maybe we should remove well 4 from the data set just because the operating conditions are different. Okay, and you can also look at the equivalent circulating density and downhole pressure and mud flow and everything else. Let's take a closer look at well 1, well 4, and the entire uh, data set. So we have an error over here. So this is a matrix scatter plot of the rate of penetration, weight on bit, torque, and the RPM associated with well 4. And so if you're looking at the RPMs associated with well 4, tells us pretty much the same story, that the RPMs are fairly high, but fairly high compared to what? Let's take a look at the entire data set. In the meantime, let's also look at well 1. And if you look at well 1, we can also see that the torque values associated with well 1 are somewhat high. Uh, you would see that these are somewhat high when I look at the rest of the data set, which does not contain well 1 and does not contain well 4. So in this case, this is the entire data set except for wells 1 and 4. And we can see the torque values, we can see the weight on bit values, we can also see the RPM values, and we can see largely the RPM values are between approximately 20 or 30 RPM going all the way to 200, with a few points slightly higher. Up over here, the weight on bit, most of the points seem to belong, and likewise with the ROP as well. There's appear to be a few points which seem to extend out from the bulk of the data set. And again, I do not know why this is happening, but at this time, I will likely remove those few points uh, for the rest of my analysis. But scrolling up again, we can now see that the torque associated with well 4, sorry, well 1, and the RPMs associated with well 4 are significantly high in comparison to the rest of the data set. So something else was going on, and it was likely not a lithological response. So we're going to remove these wells from our analysis and continue on. So we'll remove those few points that seem to be sticking out from the rest of the data set, as well as these unusually high RPM values over here. Uh, and finally, we're going to do a matrix scatter plot of the entire data set. And we are going to be coloring all the points based on the facies that they're associated with. So the story so far, we examined our entire data. We looked at how each one of the input features varied across each one of the wells. Um, we removed wells that exhibited unusual behavior, and we removed them because we don't really understand why there were those anomalous responses. I would not call them outliers at this point, but in any case, because I'm unsure of what was going on, I'm going to remove them from the data set. In all likelihood, those unusual values are probably tied to um, some operational considerations. We also removed a few other data points that didn't seem to belong to the data set. And finally, this is what we end up with. And keep in mind, for the purposes of visualization, I'm only showing four of the input features, which is rate of penetration, weight on bit, torque, and the RPM. And I'm coloring all of the points based on the facies label. And just visualizing this data set, it, it it seems like it would be almost impossible to construct a decision boundary that would take in ROP and weight on bit, for instance, and separate out the three classes. There doesn't seem to be any plane that separates out these classes, or any visually apparent curvilinear surface. But yet, we would be able to construct a reasonable supervised classifier. And I'll show you that as we scroll down through this workbook. We're going to select our input features and our target variable. And we can also look at the proportion of the facies within the data set. Facies 0 constitutes about 70% of the data set. Facies 1 is about 25%, and facies 2 is about 10%. So this is just something to keep in mind. The reason why we want to keep this in mind is because when we are going to be doing a training and a test split, we want to ensure that we are splitting our data in into a training and test split, each of which has the same proportions of the facies as the original data set. What we do not want happening is a training and a test split that looks like this, where the whole data set has the facies proportions given by the panel on the left. And perhaps when we do a training and a test split, which is done entirely randomly, we may end up with facies proportions in the training set that look something like this, and in the test set that looks something like this. And if we ended up with a training and a test split that look like this, then during training, our model is going to be seeing an abundance of facies 1 and facies 2 and very little of facies 0. Whereas when I take that model for validation or for testing, it's largely just going to be seeing facies 0, and it's not going to be seeing facies 1 and 2. And in a situation like this, more often than not, irrespective of how complex your model is, the model is going to fail. just because the model cannot generalize to the test data set. And that's because the test data set looks nothing like the training set. All right. So what we're going to be doing is we're going to be doing a stratified split, and we're going to stratify it based on the facies proportions. We're also going to scale our input features. And finally, we're going to be choosing neural network classifier. And for demonstration purposes, I'm going to be choosing a neural network classifier with 4 hidden layers. Each layer has, or rather, the first layer has 30 hidden neurons, the second has 30, the third has 20, and the fourth has 20. Where did I get these numbers from? I just chose these numbers randomly. In a real operational scenario, we would be trying out different neural network architectures. All right, so I'm going to define my neural network model, and then I'm going to fit it to my training data set. And this is going to take some time because if you look at how many neurons I have, then I'm going to have 30 times 30 times 20 times 20 uh, weights at least, plus another 30 on the input side and another 20 on the output side. So that's quite a few weights, and we'll also have the corresponding biases. I also do want to emphasize that because this is a classifier that's going to be outputting the probabilities associated with each label or each class, we are going to be having 3 outputs. The first output is going to give us, for a specific input data point, it's going to give us the probability that it belongs to class 1. The second output is going to tell us what's the probability that it's associated with class 2. And the third one is going to tell us what's the probability that it's associated with class 3. And of course, the final answer is going to be the label associated with the maximum probability. So we have all of those weights and we have all of those biases that need to be trained, that need to be calibrated. And finally, now we have a trained model. We're going to see how well this does on test data. So we're going to be looking at accuracies. We're going to be looking at classification reports. So specifically, my accuracy is about 95%, which is pretty good. But it's pretty good, but I don't know whether I could have found a better model because I haven't tested any other model yet. And the second thing I want to mention is that accuracy is not the primary metric we're going to be looking at. When I have infrequent classes, accuracy can perhaps paint a distorted picture of what classification is doing. And really what I want to be looking at is the F1 scores associated with each one of the classes. And I have relatively high F1 scores, which means that my precision and my recall associated with the identification of label 0 is high. The precision and recall associated with the identification of label 1 is high, and the precision and recall associated with the classification of label 2 is also high. I can again reframe that information using a confusion matrix. And this is my confusion matrix where I have the true labels on this side and the predicted labels on the horizontal axis. And largely this is a diagonally dominant matrix with very few misclassifications on the off-diagonal terms. So when the true label was 0 in the test data, my predicted label was 0, or the classifier predicted the label 0 roughly about 6,200 times. It got it wrong about 120 times and said it's label 1. and about 70 times it said it's label 2. And on the face of it, this seems like an acceptable performance for my classifier, but I don't really know that until I test this against other classifiers as well. And this is what we do with training and test splits. So just to recap what we did, we uh, had our data organized by the input features, which consists of my drilling data, and at each corresponding, and we also had the facies labels corresponding to each data point. And our goal was to construct a classifier that relates the drilling data to these labels. We cleaned up our data set. We removed meaningless information associated with negative rate of penetration and weight on bit values. We also cleaned up our data set by examining the data on a well by well basis and removing wells that we thought showed some anomalous responses. And then finally, we used a training and a test split and constructed a neural network classifier that showed admirable performance against the test data set. And while this is a reasonable workflow, this is typically what this is not uh, typically what we do. What we do instead is we try 3 or 4 or 5 or 6 neural network architectures, and we apply them to our data set and we see which one is the best. So far, what we did was I chose 4 layers and I specified how many neurons are present in each layer. And although I got a decent performance out of it, I don't know that that's the best model. So what we're going to be seeing next is where I'm going to be making a choice in amongst 3 different models. And I'm also going to be doing something called cross-validation, which we have discussed previously. And I'll go over cross-validation in a little bit more detail as we progress down below. So I'm going to scale my input drilling data, and we're going to be using 5-fold cross-validation. Now for 5-fold cross-validation, this is what the setup looks like. I'm going to use a stratified split and break up my data set randomly into 5 different folds. And I'm going to end up with uh, 5 different subsets of the data. And then I choose split 1. In split 1, I choose one of the folds to be my test data set, and I train a model against the remaining 4. With split 2, I choose another fold as my test data set and train the model on the other 4. And I repeat this process successively. And you can see that in each split, the choice of test data set is different. The choice of training data set is different. And what this allows us to do is it allows us to examine the model to see if the model is uh, adapting and generalizing well to different test data sets. You can see that with each one of these splits, my test data set is completely different. And so any anomalous response with respect to any test data set would stand out and would essentially tell us that the model is not generalizing well to new data. Okay, so let's see this in action. We're going to create 5 different splits in my data, and then we're going to successively take split 1, keep my test data set aside, and train the model on the remaining 4. And then with split 2, I have another holdout data set, and I train my model on the remaining 4 folds. With split 3, my test data set is a different fold, while my training data set is different. And then I have split 4 and split 5. So that's 5-fold cross-validation. And the advantage of cross-validation is it helps us diagnose overfitting or underfitting. And it also helps us verify if a model does well on unseen data. And it also allows us for something called hyperparameter tuning, which we haven't talked about yet, but that is something to keep in mind. And we'll explore hyperparameter tuning in greater detail in subsequent lectures. Okay, so for this task, I'm going to be choosing between 3 different neural network models. I have network 1, I have network 2, and I have network 3. Uh, for the purposes of illustration, I'm just showing one input node, but really I have 7 input nodes corresponding to each one of the 7 input features. And I have 3 output nodes. The 3 output nodes correspond to the probabilities associated with each of the classes. So 3 output nodes, which essentially tells me what the class label should be for any given input data point. So how do I specify that? I specify a variable called parameters, and I specify the first model to contain 3 neurons in the first hidden layer, 3 neurons in the second hidden layer, then the second model with 5 neurons in the first hidden layer and 10 neurons in the second hidden layer. And then I have the third network, which has 5 neurons followed by 10 neurons. And what I'm going to be doing is I'm going to be applying or using a neural network classifier, and I'm going to be using 5-fold cross-validation to evaluate these different models. And how I'm going to be choosing the best model is using the F1 score. And in this specific case, I'm going to run this on all of my data, on my entire data set. So this is going to take quite a bit of time because I have 3 different models and I have 5 different folds, which means that I'm going to be performing 15 different model fits. So we're going to run this, and we'd have to wait for a time to get some results. Now we're finally done with that. Uh, and of course, we've tried the 3 different models with 5-fold cross-validation. We don't know which one is the best. So let's go ahead and see which one is the best. So what I have is model 0, which had 3 neurons in the first layer and 3 neurons in the second layer. Gave me an average F1 score of 0.71, and it's ranked the third best model. And the best model actually had 5 neurons in the first layer, 10 neurons in the second layer, with an F1 score of 0.8 approximately, and that was ranked number 1. Now there's another attribute of these models that I'm printing out, which is the standard deviation in the test scores. So we are doing 5-fold cross-validation, and we want the model performance to be equivalent across each one of the 5 folds. We do not want the model to be sensitive to the choice of test data. So we not only want a high average test score, we also want a relatively low standard deviation in those test scores across each one of the 5 folds. And you can see that the model with 5 neurons in the first layer and 10 neurons in the second layer seems to do remarkably well. And the moral of the story is that just because you choose a model with additional complexity, which is the model with 3 layers, 5 neurons in the first layer, 5 neurons in the second layer, and 10 neurons in the third layer, does not mean you're going to get uh, commensurately better performance. Sometimes more complexity is disadvantageous. And so we have the best model over here. We again just want to verify that the best model is indeed the best model and does well across all of the 10 folds. So we're going to evaluate this model on my data set and check and see that whichever metric I'm choosing for evaluation, which happens to be the F1 score in this case, is equivalent across all of the 10 folds, as opposed to a model that behaves something like what we're seeing in this figure over here, where the performance varies quite a bit across each one of the 10 folds. We can see that with certain folds, the model performs really well, and with other folds, the performance is a little bit weaker. And this means that the model is sensitive to the choice of test data. So we're going to choose our best model, and we're again going to be applying it to our drilling data, and we're going to be doing tenfold cross validation. This again is going to take some time. So while this is running, I also want to mention that each one of these three different models did not do as well as the model that we initially tested, which had 4 different layers. And that's fine because I was simply illustrating what five-fold cross-validation or what the process of k-fold cross-validation is about. We chose 3 different neural network models to evaluate, and 3 is not a large number by any means. Typically, we would evaluate about 6 or 7 different models. In fact, what we saw previously was that we got pretty good performance with the 4-layer model, which had 30 neurons in the first layer, 30 neurons in the second layer, 20 and 20 in subsequent layers. Uh, and perhaps we should have tried neural networks of comparable complexity or slightly higher complexity. What I chose to illustrate was whether we're able to accomplish something um, approximately the same with networks of lower complexity. And it turns out that in terms of the F1 scores, no, we were not able to achieve that level of performance, and that's fine. But this whole process of evaluating these 3 different models gave us some insights into what we should perhaps be trying next. Maybe we should evaluate a fourth network, which has 4 layers with a different set of different numbers of neurons in their hidden layers. Maybe even try a 5-layer network, and so on and so forth. Of course, there's going to be a point in time where we have to ask ourselves, at what point do we stop testing? Because there are infinite number of combinations that we could possibly test. And that's largely dictated by how much of computational power and resources we have available to us. Uh, in general, we would be testing out about 7 to 8 different models. Something that's a good starting point would be to choose something that has low complexity, very high complexity, and something that has intermediate complexity for the problem at hand, and seeing which of these models does better, and then slowly zooming in on a model with the appropriate complexity using 5-fold or 10-fold cross-validation. So we were running our 10-fold cross-validation, and it's still going on because we are fitting 10 different models with the corresponding model architecture against our data set. And depending on the kind of system you're running, it can take a very long time, or it could be a rather rapid solution. So Once this is done, we're going to plot the F1 scores associated with each one of the 10 different uh, folds, or the tests against each one of the 10 different folds, and check and see if the model performance is more or less associated with low variability across the 10 folds, or whether it's associated with relatively higher variability across each one of the 10 folds. If we see something that looks like this, then the model choice that we made is definitely not a good choice. We should go back and re-examine maybe 2 or 3 other models before we come down and choose a specific neural network architecture. There are other parameters that we can tune in a neural network. And for right now, we are keeping most of those parameters fixed. We're using the default options because the entire objective of this uh, Jupyter Notebook was for you folks to see how a neural network can be used for complex classification tasks, and to also illustrate the methodology for um, tenfold, for k-fold cross-validation, and how to choose the best model from in amongst several different models. It looks like our tenfold cross-validation is done. We'll look at our F1 scores across each one of these 10 tests. And what we see is that the performance of the model is not equivalent across each one of these 10 folds. And this tells us that the model is not generalizing well to new data. This is a model that is biased in some fashion. It's showing excessive variability with respect to the test data set. And so I should probably go back and then restart this entire process by choosing a different set of models over here. I know that something with relatively low complexity, like 3 neurons in the first layer and 3 neurons in the second layer, is insufficient. So I'm probably going to explore models with a little bit more complexity, go through this process of 5-fold cross-validation, and eventually end up with a model that shows very good variability, or very less variability across all of the 10 folds. And that's the end of this specific discussion, where we applied neural networks to drilling data so that we can perform reservoir characterization tasks.